right. In this session, we're going to cover the expectation and the variance and standard deviation of a random variable. Okay? So these are quantities which help us to characterize random variables. And the expectation and the variance would be sort of the, if I was introduced to a random variable, these would be the two things that I would really want to know. There are other measures, but perhaps you would see them in later courses. So the expectation is something like an average. And we'll discuss what variance is a little bit later. So let's imagine this. We toss 100 coins into the air. Okay? How many heads do we expect to come up? We're recording heads and tails. How many heads do we expect to come up? 50 out of 100? Okay, we can, and then we would say, well, it's not always going to be 50 out of 100. Sometimes it'll be a few more or a few less, right? So we wouldn't be surprised to see 53 heads or 47. What about 70? How likely would that be? So we're going to be exploring, going forward, we're going to be exploring these kinds of ideas. What's the expected, what's the expectation of a random variable? How much variance can we expect around that? How likely is a certain amount of variance going to be? These will all be important topics as we go forward. Okay, so let's start by giving the definition. So first we give it for a probability, a random variable that has a probability mass function, a discrete random variable. Then we'll talk about the expectation for a continuous random variable that has a probability density function. So you have a discrete random variable x, and we write the notation for its probability mass function is small f sub x. And then the notation for its expectation, we either write mu subscript capital X, or we write e of x in square brackets. They both mean the same thing. And what we do to calculate this, so this is a real number, we sum over all the allowed values of x. Of x, the values that the random variable capital X takes, small x, times the probability of taking that value. Okay? So, in the continuous case, you have a continuous random variable capital X. It has an expectation which is either written as mu sub x or e of x, and that's given by integrating over all the reals the value small x times the PDF evaluated at x dx. Okay, so these are the definition of expectation in the continuous and in the discrete case. Okay. Yeah.
In both continuous and discrete cases, is the f of x supposed to be the PDF or the PMF?
No, yeah. So in this case, it's the PMF, and in the continuous case, it's the PDF.
In terms of notation, what is the difference between a PMF and a PDF? How do you differentiate?
A PMF is for a discrete random variable, and it represents a probability. A PDF is a probability density. It's not a probability.
Is there any difference in how we write them?
Well, we would have to define these in different ways, right? Okay. So we're going to toss a coin twice. This is the sample space of the results. We're recording heads and tails. The random variable x is the number of h's that you get. Okay, so that's a discrete random variable. Okay, so what's the probability of getting 2 h's? One outcome out of 4 equally likely outcomes, 1 by 4. What's the probability of getting exactly 1 h?
1 by 2.
Right. 2 outcomes out of 4 equally likely outcomes, 2 by 4 or 1 by 2. What's the probability of getting exactly 2 t's?
1 by 4.
Right. 1 outcome out of 4 equally likely outcomes, 1 out of 4. Okay, so this is how we write the PMF for that x. Right? And I should have written here 0 for any other value of x. Okay? All right. So now that we have the PMF values, so we have the PMF defined for us, we can now calculate the expectation for that random variable, E of x, or we also write mu sub x for this. Okay? So it's the sum of x times the PMF evaluated at x. Okay, so we could have 0 h's times the probability of 0 h's is 1 over 4, same as the probability of 2 t's. We could have 1 h times the probability of 1 h, we said was 2 out of 4, plus we could have 2 h's times the probability of 2 h's, we said was 1 out of 4, and this is 1. This sums to 1, right? There are no other possible values for x. Okay, so that's what that says. The expected number of h's is 1. Is that okay? All right. Now, let's try another one. So for the exponential random variable, recall we had this discussion before. We calculated this. So the exponential random variable has a PDF small f sub x, or it also has a cumulative capital F sub x, and we calculated that the CDF for the exponential random variable could be defined this way. Okay, so there's the CDF. All right. Now, how can I find the expectation of that? Okay, I mean, what does expectation look like? For the expectation of a continuous random variable capital X is you evaluate the integrate over all the reals, x times the PDF for x dx.
So it's a differentiated number.
Right. So in order, if I forgot what the PDF was, but I've been given the CDF, I can always differentiate the CDF to recover the PDF. Remember, this is in 2 parts, right? So you'd say that for x greater than or equal to 0, the derivative of 1 minus e to the minus x, that would be the PDF for x greater than or equal to 0. And then the derivative of 0 would be the PDF for the rest of the real line. Okay? So we differentiate 1 minus e to the minus x, and we differentiate 0 to get 0. And now we have the PDF for the exponential random variable defined for us. Okay. Now how do we find the expectation? The expectation for a continuous random variable, x, is found by integrating from minus infinity to infinity, all possible values of x, times the PDF evaluated at that x, dx. Okay? Now the integral from minus infinity to 0, this PDF has the form 0, remember? So there's no point in integrating 0. So we're just going to integrate from 0 to infinity. And on the interval from 0 to infinity, the PDF has the form e to the minus x. So we're going to get x times the PDF from 0 to infinity. Okay? And then the final, the integration that you could be done by parts, for example, to do that. Okay? You should check that you do know how to integrate by parts in case you've forgotten, because the exponential random variable is going to show up again later, and you're going to have to do integration by parts. Okay. So that was the expectation. Now, the expectation is insufficient, right? So we can imagine that we have, say, something like the bell curve. And we have an expectation which is 0 in this case. And we've got something else which is, maybe it has the same expectation, but it's more strongly peaked. And as you go away from 0, it dies off faster. So there's this one graph of the PDF. There's another graph of a PDF for another random variable. Okay? Now, the variance gives us an idea of how far away values are likely to occur from the expectation. So you have the expected value. You don't always get exactly the expected value. You get values around that. So how broadly distributed are the values that you're going to get away from the expectation? So that's given by the variance. Okay, so this is what we want to discuss. Along the way to defining the variance, we need to talk about we've already talked about the expectation of a random variable. We need to talk about the expectation of a function of a random variable. So we're going to, functions of random variables. So if I had x as a random variable, and then I said something like 3x squared. Well, that would also be a random variable because it's a function of x, which is random. Okay? So, for example, let's say we have a PDF for some random variable capital V, and the function is given like this. Then if I calculate its expectation, I take the integral from minus infinity to infinity, v times the PDF evaluated at v. Well, this is an even function. And this is an odd function over a symmetric interval. So that's going to integrate to 0. Okay? Otherwise, you could sit down, you could actually do the integration, but it's easy in this case to see that it integrates to 0. So fine. Yeah. This is an odd function. If you put in f of the PDF evaluated at v and the PDF evaluated at minus v gives you exactly the same number. Okay? Now, what if I multiplied this thing by v? I have v over root pi e to the minus v squared. Well, that new function, that integrand, evaluated it at v and at minus v, differ by a minus sign. So when f of x equals f of minus, when f of x equals minus f of minus x, then we say that the function is odd. So if f of x equals f of minus x for all reals, we say that it's an even function. If f of minus x equals minus f of x, we say that it's an odd function. If you integrate an odd function over a symmetric integral, if you integrate from x equals minus a to x equals plus a, some f of x dx, well, and this integrand is odd, then it integrates to 0. Okay? There's as much area above the curve as there is below the curve, basically. Above the axis, between the axis and the graph, and the graph below the, right? Okay? So I can, in this case, I can immediately, if I have v times what that, this was an even function, so then I multiply by v, that will give me an odd function, right? Because the product of an odd function and an even function is an odd function. So this overall is odd, and I'm integrating over a symmetric interval, and I'm going to get 0. Well, like I said, if that argument doesn't satisfy you, you could work out the integral, and it would work out to 0. Okay? So if I'm interested in the kinetic energy, so these were related to velocities of molecules in a gas. If I'm interested in their kinetic energy, I'm interested in v squared, the velocity squared. Okay? So the expectation of v squared, the way we, right? We calculate the expectation of v squared as being the integral from minus infinity to infinity of this value v squared times the PDF at v. Okay? So if this was some general function of v, if this was g of v, for example, then we would integrate minus infinity to plus infinity g of small v times the PDF evaluated at v. In this case, we get 1/2.
Sir,
Yeah.
v squared times the, I think that was the velocity integral.
Yeah.
So what to say, this one's an even, so e of v squared.
Yeah.
इसका सही इंटीग्रल निकालना पड़ेगा। और
Yeah.
इंटीग्रल निकालने के लिए सिर्फ पोलर कोऑर्डिनेट्स आने चाहिए, तो वो तो सर बड़ा ऑप्शन है। तो in this case given होगा फिर क्या?
No, but you've got a v squared here, and you've got a v squared up. Well, okay. Yeah, it's an even function. Yeah, you'd have to make some effort to calculate. Yes.
You should have knowledge of carry 2 to the integral.
Okay.
Because it is.
All right. I will try to not ask you to do integrals that you couldn't possibly do, okay? Okay, so as I was saying, yeah.
Just to backtrack a little bit more, the initial PDF of the random variable d,
Yeah.
is that an odd function or an even function? This one.
This is even because if you put in v or you put in minus v, you get the same number. So that's even. Now you multiply it by v, so you're multiplying an odd function by an even function, so you got an odd function overall. Okay? So, x is a random variable. It has a PMF f sub x. G is some function of the random variable. then we say that the expectation of g of x, or e of g of x, you sum over all the allowed values of x, g of small x times the PMF evaluated at small x. Okay? So that's the expectation of a function of a discrete random variable. Okay? So that's the discrete case. What do you think we do in the continuous case? Well, we do the integral, right? Right, so if x was continuous, then we would calculate the expectation of g of x by integrating over all reals, g evaluated at small x times the PDF for x evaluated at small x. Okay, so that's the expectation of a function of a continuous random variable. Okay. Any questions so far? Okay, back to the same example. 2 coin flips, or flip a coin twice, and x is the number of heads. Could be 0, 1, or 2. This is how we would define the PMF that we discussed before. And this time, we already calculated the expectation of x. This time, let's calculate the expectation of x squared. Okay? So how do we do that? We sum over all the possible values of x squared times the probability, right? Times the probability of that x occurring. Okay? So the expectation of x squared is given by summing from x equals 0 to 2. There could be 0, 1, or 2 h's. X squared times the probability of that value of x occurring. So it's 0 squared times the probability of 0 h's, plus 1 squared times the probability of 1, plus 2 squared times the probability of 2, and that sums to 3 halves. Okay. We're going to use this in our calculation of the variance of x in a bit. Okay. So a few things that might make your calculations a little bit easier. We'll say A and B are reals. X is a random variable, which has a well-defined expectation. Then we have this property. If you already know how to calculate the expectation of x, you can calculate the expectation of ax plus b as a times the expectation of x plus b. And the reason you can do that is because summation has this linearity property, right? If you go back to the definition of summation, right? So the expectation of ax plus b is equal to the sum over all the allowed values of x, a times the allowed value of x plus b times the probability of that value of x occurring, right? But you can, if you have a sum in here, if you have two things summoned inside the summation, then you can break things up, right? So this is equal to summation over x, ax times f sub x, plus the summation over x, b times f sub x. Is that okay? That's just a property of sums. Well, another property of sums is that you can pull a constant outside. A constant multiple can be pulled outside of the sum. So this is a times the summation over allowed values of x times f sub x times the PMF, plus, well, okay, this is b, is a constant multiple, so I can pull this one outside also. Okay, what is the summation over all allowed values of x times the PMF evaluated at x? That's the definition of expectation. So this part is the expectation. Okay? And the PMF is a probability, right? Remember, one of the properties was that if you add up all the probabilities, you're supposed to get 1. So this is B. Okay? So if you have a linear function of x like this, and you already know how to calculate the expectation of x, you can find the expectation of this linear function of x. Is that okay? All right, now let's see about, come back to this one. The PDF for this random variable v is 1 over root pi e to the minus v squared. We gave an argument why the expectation is equal to 0. What if I asked you, what's the expectation of m times v minus 3? Right. According to that rule we just saw, expectation of ax plus b is equal to a times the expectation of x plus b. Apply the same rule here. You get m times the expectation of v, which is 0. And then you've got a constant of minus 3. So 0 minus 3. Yes?
सर वो जो आपकी लास्ट लाइन है
Yes?
एक के साथ EFX बन गया बट जो B की जो समेशन थी वो कितनी है?
Well, this part is the sum of probabilities, so it's equal to 1. Okay? Okay, so once again, it has this linearity property. You can pull the constant outside. You can take m times the expectation of v. We found that this was equal to 0, so this works out to be minus 3. Is that one okay? All right. Okay. Let's try another one. We roll a fair die, 6-sided die. X takes the value plus 1 if the result is even. X takes the value minus 1 if the result is odd. And let's calculate the expectation of x and the expectation of x squared. Okay? What's the PMF? Well, half the possibilities are an even roll. Half the possibilities are an odd roll. You can only get even or odd, so there's no other possibility for the values that x can take. Okay? So, the expectation of x is the sum over all the allowed values of x, small x times the PMF evaluated at small x. Okay. So it can take x can take the value plus 1. The probability of plus 1 is 1/2. X can take the value minus 1. the probability of x being -1, rolling an odd, is 1/2. You add these together, you get 0. So the expectation of that x is 0. Is that okay? All right. Expectation of x squared. Well, by definition, that's a sum over all the allowed values of x, those values squared times the probability that x takes that value, by the definition of the expectation of a function of a random variable, of a discrete random variable. Okay? X can take the value +1, square that, times the probability, times the PMF evaluated at +1. X can take the value -1, square that, times the PMF evaluated at -1. Okay? That sums to 1. So we found the expectation of x was 0, and the expectation of x squared was +1. All right, I think I'll leave one problem for you to do. The answers are there. So you do it and you see whether you're understanding properly. Okay, some more properties of the expectation. We already saw this one. A linear function of x, ax plus b, is the same as a times the expectation of x plus b. Okay? If you have the expectation of two functions, the sum or the difference of two functions of a random variable, expectation of g of x plus or minus h of x, well, that's the expectation of g of x plus or minus the expectation of h of x. Why is that? Because, well, if you've got sum an plus bn, you can break that up as the sum of an plus the sum of bn. That comes from the properties of summations. Okay. Variance. Okay, so as I said before, variance is a measure of how far our values are likely to, well, it's a measure of how far values lie from the expectation. Okay? So sometimes you have random variables and all the results most of the time are very close to the expectation. Other random variables, you can have things that are more spread out. Okay, so in the discrete case, the variance is, we write one notation is sigma squared sub x. That's the variance for x. It's given, we also, okay, should have written this down. We also write var of x for the variance. Okay, you should know both notations. Okay, and how you calculate it as the expectation. So you take x, you have your random variable x, your discrete random variable x. Now subtract from that the expectation, and then you square it. So you sum over the squares of all the differences from the expected value. So it tells you, it's a measure of how far values get from the expected value of x. Okay? And by the definition of the expectation of a function of a random variable, this is the sum over the allowed values, x minus the expectation of x squared times the PMF evaluated at x. Yes?
This is not standard deviation.
This is not quite the standard deviation. This is the variance. Okay? But yes, standard deviation is related to this, yes. Okay.
Please explain how that is identical.
Oh. From you, well, the expectation is a summation of that over all x, of that function evaluated at that x, times the PMF at x. Okay? So in general, the expectation of g of x is the summation over the allowed values of x, g evaluated at that value, times the PMF evaluated. So that's what we've done over there. Okay?
Sir, mu is just the mean.
Okay. Mu is what?
Just the mean.
Uh,
Or the expected.
okay, mu is, yeah, mu sub x is the expectation. Sigma squared sub x is the variance. Okay? Okay. In the continuous case, well, we do integrals instead of summation. So this time we integrate over all reals, x minus the expectation of x squared times the PDF evaluated at x dx. Okay, so it's the analogous integral. All right. Okay, and once again, this is a square of the difference between the expected value of x and the value that x is actually taking. Okay? And by squaring then we're sort of saying it doesn't matter whether you're 5 over from the expectation this way or you're 5 over from the expectation that way. We square that to get 25. Okay?
Why don't we use modulus instead?
Yeah, well, some people do. Some people would use the modulus also as a measure of, well, okay, sorry. Some people, we shouldn't say modulus, the absolute value of the difference. Yeah, some people do use that. But you won't get exactly the same number, right? But yes, I mean, we could take the absolute value of the difference. We could take an even power of the difference. Yeah, there would be different ways of measuring how far you're getting from your actual, how far your actual values are from the expected value.
The value of the variance wouldn't be the same.
Oh, yeah.
If I squared that value, would it then be the same variance?
No, if you have other ways of measuring the difference, you're going to get a different number. And we won't call that the variance, we'll call it something else. Okay. Standard deviation then is related to the variance. It's the square root of the variance. Okay? So quite often we talk about numbers being this many standard deviations away from the expectation. Okay, so continuing with the same example, x is the number of heads found in tossing a coin twice. Okay, we want to find the expectation, we want to find the variance, and we want to find the standard deviation. Okay. This was the PMF. We already found that. As I said, I should write 0 otherwise. Okay. So, x can take values 0, 1, and 2. So the expectation of x is those values x times the PMF evaluated at x. So 0 times the PMF at 0, plus 1 times the PMF at 1, plus 2 times the PMF at 2. And we get 1. We expect 1h in 2 tosses. Okay. Now, the variance is the expectation of x minus the expectation squared. Okay? So, x can take values 0, 1, and 2. We sum over those. The actual value x minus the expectation squared times the PMF evaluated at that actual value. So you get, okay, you could get a 0. So 0 minus the expectation squared times the PMF at 0. Plus, you could get a 1. 1 minus the expectation squared times the PMF evaluated at 1. Plus, you could get 2 h's. 2 minus the expectation of x squared times the probability of the PMF evaluated at 2, and that all sum up to 1/2. So that is the variance of x. So what's the standard deviation of x? Right. It's the square root of 2. Right? Remember, we write variance as sigma squared. We write standard deviation as sigma to emphasize that the standard deviation is the square root of the variance. Okay? So we got that the variance was 1/2. So the standard deviation is 1 over root 2, the square root of that. Okay, now there's another way of doing it. Right? It turns out that the expectation of x minus the expectation of x, all squared, okay, can also be calculated as the expectation of x squared minus the expectation squared. Okay? There's a bit of algebra involved in proving that, so you should try it as an exercise to see that you understand. But from the properties of summations or the properties of integrals, you should be able to prove this. Okay? So do this as an exercise. Going back to the definition in terms of a summation or in terms of a integral. Okay? So if we were to go through that exercise again, right? So what would we, if we want to do it this way, we would find the expectation of x squared first. It works out to 1/2. And then we would subtract off the expectation squared. We already found that the expectation was 1. And again, we would get that the variance is 1/2. So whatever is convenient for you, right? You can calculate the variance in these both these ways. And then you can take the square root to find the standard deviation if that interests you. Okay. Now, we discussed the expectation of a function of a random variable. So we'd like to also to discuss the variance of a function of a random variable. So if x is a random variable, g of x is some function of the random variable, then its variance is given by, you take g of x, you take the expectation of g of x minus the expectation of g, and you square that, the expectation of all of that. Or you have g of x squared, take the expectation of that minus the expectation of g squared, just like you have over, similar to what you have over there. Okay? And again, you should be able to show this for yourselves, going back to if you start from the definition of the expectation as a sum or as an integral. Yes.
Shouldn't that be g of x squared, like the Jones square against identified?
No. No, this is the new random variable is g of x, and that's what I'm squaring. Okay. So remember we already had this property. We had the property, for example, that expectation of ax plus b was the same as a times the expectation of x plus b. Okay? Now, supposing that I know how to calculate the variance of x, let's say I knew how to do that, and I already knew this number, then if a is a constant, what's the variance of ax? Okay. Well, the claim is that the variance of ax is a squared times the variance of x. Okay. So let's see, how would that happen? What's the variance of x? Right. It's the expectation of x squared minus the expectation of x squared. Right? Okay. Well, then the variance of ax is the expectation of ax squared minus the expectation of ax squared. Okay? But ax all squared is the same as a squared x squared, right? So this is the same as a squared x squared over here. Okay. The expectation of a constant times the random variable is the same as the constant times the expectation of that random variable. Right? So I can pull the a squared outside over here. So this is a squared times the expectation of x squared. Now, what's the expectation of ax in terms of the expectation of x? It's a times the expectation of x, remember? By the linearity property of expectations. So the expectation of ax is a times the expectation of x. So let's replace that by a times the expectation of x squared. Okay, well that's the same as a squared times the expectation. So this is a squared times the expectation squared. Okay. Well, there's a common factor of a squared here. So let me take this out. Have this as a bracket. And what's this? That's the variance. So the variance of ax is a squared times the variance of x. That all right? Okay. Let's look at the variance. So try this one on your own. the variance of ax plus b is a squared times the variance of x. Okay? You can, the same sort of calculations that we did over here will give you this result. You should try a few of these to make sure that you understand. Okay. So now we come to Chebyshev's theorem. Okay. And what Chebyshev is doing is it's saying how likely is it that you're going to get results which are more than this many standard deviations or this much variance away from the expectation. Right? So Chebyshev's theorem puts a bound on how far. Basically, it says that getting a result for x, which is many, many standard deviations away from the expectation of x, getting such a result is unlikely, very unlikely. Okay? Okay? And this works for all random variables. So that's the surprising thing. If you know specifically what the random variable is that's involved in your problem, then you know what the random variable is means you know what the PMF or the PDF for that is. And then you can get very precise results. Okay? But Chebyshev is giving you a bound that works for all random variables. And sometimes you don't know, when you're doing your experiment, you don't know what the underlying random variable is. Okay? So I might be doing a survey. That's my experiment. Right? I don't know what the underlying variable for a human being is. Right? But I can still get bounds on my survey results, for example. Okay. So here's the theorem. The probability that any random variable x will take a value within k standard deviations of the expectation is at least 1 minus 1 over k squared. And it can be larger than that. Okay? So the probability, for example, that I have a random variable x, and after doing the experiment, x is found to have a value which is within 10 standard deviations. Let's say we're looking for the probability within 10 standard deviations. That probability is 1 minus 1 over 100. So there's a 99% or better probability that the random variable x will take a value within 10 standard deviations of its mean, of its expectations. Okay, so this is the way we write it. The probability for any random variable, x, the probability that x is taking a value which is k standard deviations less than or k standard deviations more than the expectation of x, that probability is greater than or equal to 1 minus 1 over k squared. Okay, so for example, the probability that x takes a value which is somewhere between k standard deviations less than x up to k standard deviations more than x, the probability of that is greater than or equal to 1 minus 1 over k squared, and it doesn't matter, this holds no matter what the random variable is. How's that?
It's from x, so whatever. So if I conduct an experiment
Yeah.
and I need to be k standard deviations below.
Okay. All right. So let's just maybe if I draw something here. Okay. So let's say x can take all sorts of values. Here's its expectation somewhere on the real line. Okay? And then I count off 2 standard deviations. So this is mu x plus sigma x. This is mu x plus 2 sigma x. This is mu x minus its standard deviation of x. This is the expectation minus 2 standard deviations. Okay? So, Chebyshev says that the probability that you were somewhere in here between minus 2 standard deviations less than the expectation up to 2 standard deviations more than the expectation, the probability of that is 1 minus 1 over 2 squared. So 3/4. The probability that you are within 2 standard deviations of the expectation of the random variable is definitely equal to or bigger than 75%. Right? Okay. So if we are doing an experiment, we have this apparatus, it's looking at cosmic rays or something, and we get a number that's 12 standard deviations away from the expected value. We expect an error in the experimental apparatus or in our measurement, right? Rather than, okay? Okay, so what about 1 standard deviation? Chebyshev says that the probability that x is taking a value from 1 standard deviation less than the expectation to 1 standard deviation more than the expectation, Chebyshev says that that's greater than or equal to 1 minus 1 over 1 squared. Okay, that's 0. The probability that it lies within 1 standard deviation of the expected value is bigger than 0. So Chebyshev doesn't help us there. Okay. What's the probability of 2 that the actual value that when you do the experiment, the value that you see for x is from minus 2 standard deviations less than the expected value to 2 standard deviations more than the expected value? What's the probability that it lies in this interval? Well, that's bigger than or equal to 75%. Right? Okay. What about 3 standard deviations? So mu plus 3 standard deviations bigger than x, and here's 3 standard deviations less than x. The probability of that probability of x taking a value in this interval is greater than or equal to 1 minus 1 over 3 squared. Yeah, so about 90%, let's say. Okay? All right, so if you're running an experiment and you're continuously getting results for x, right, oh, so you're doing the same experiment over and over again and the results are supposed to be independent, and you're getting values that are, you know, 4 standard deviations away from the expected value, then you need to rethink things and, you know, check your apparatus or check your measurements or maybe check your calculations of the expectation. Okay. Chebyshev says that the actual values of x, that the values that x takes, are close to the expected value. Okay. All right then. Any questions? No? Okay. See you later.